Okay, so what we have here is number 6 from the McGehee text, and we have a situation in which we have a uniform electric field of 5,000 newtons per coulomb, and we're placing an electron right in the midst of it with an initial velocity of magnitude 10 meters per second going upwards 30 degrees from the horizontal. And for part A, it's asking what is the magnitude and direction of the acceleration of the electron while it is moving through the electric field. So that's fairly simple enough. We just set the actual force that's being caused by the electric field equal to the mass times acceleration, which is basically one of the 3 laws of forces. So we say, okay, the force due to the electric field, that has to be equal to the electron's mass times its acceleration. So therefore, the acceleration has to be equal to the force of the electric field divided by its mass, which is equal to its charge times the electric field itself times the mass. And when you multiply out, that's going to be equal to 1.6 times 10 to the negative 19th coulombs times 5,000 newtons per coulomb over 9.1 times 10 to negative 31 kilograms. And you should end up with approximately 8.8 times 10 to the 14th meters per second squared. But make sure that actually, since this is an electron, you're going to have a negative Q here because of its positive charge. See, actually, this charge, the magnitude is the same for both the proton and the electron, but since we have an electron here, the charge has to be negative, therefore this makes our acceleration negative, which means the direction is going to be going down from here. Which almost makes sense because for every rule in physics, or at least in electricity and magnetism, if you have an electric field moving upwards on a negative charge, this negative charge is going to have to go downwards. And if this was a positive charge, it would have to go upwards. So, anyway, for part B, it's saying, after entering the electronic field, when will the electron reach its maximum height? So, this can actually be turned into a interesting kinematic problem, because what's asking is, okay, so as soon as this thing's going to be launched, its pattern is going to be slightly parabolic like this, because we have negative acceleration bringing this ball down, but we also have at the same time this positive velocity. So this is just simply a kinematic. So it says, when will it reach its maximum height? Well, we know at this maximum height, the y component of the velocity will be equal to 0. And it's saying, when will its maximum height be this way? Okay, so then we can say, all right, so y sub t, that's going to be equal to negative 1/2 gt squared plus v0 initial t. And we're finding this velocity. So vf, this final velocity right here, that's going to be equal to negative gt plus the initial velocity. In this case, at this time right here, at this point, it's going to be equal to 0 meters per second. Therefore, gt has to be equal to v0. Therefore, this actual time that's going to be able to take is going to have to equal to v0 divided by our acceleration. But in this case, our acceleration is going to be the result from part A. So we'll just have the magnitude of A right here, and it's going to stay constant no matter what, because the actual electric field is uniform in all ways. So we have our acceleration here, and so we have v0, and since we can just get the y component, that's just going to be equal to 10 sine 30 degrees divided by the acceleration we got from part A, which is approximately 5.7 nanoseconds. Okay, so for part C, it says, what is its maximum height above the entry position? So we just want to find this height right here. Well, our initial component. Well, it says above the entry position, so we can assume at here this is going to be our 0 point. And where we want to find our maximum point. So for part C, let me just get rid of this. Part C, we want to know its position, so we have our position function, so y sub 5.7 nanoseconds. That's going to have to be equal to negative 1/2 a 5.7 nanoseconds squared plus 10 sine 30 degrees meters per second, 5.7 nanoseconds. That ends up being approximately 0.014 meters. D, it's asking what is its maximum, its momentum at the maximum height. Fairly simple. The momentum, P, that's just its mass times the velocity. Towards at the maximum height, the y value of the velocity is going to be 0, but not the x value. So we just say, okay, so this mass, that's going to be, we know the mass here, so that's going to be 9.1 times 10 to the negative 31 kilograms times its velocity, which is just going to be 10 cosine 30 degrees. And that ends up being approximately 7.9 times 10 to the negative 24 kilogram meter per second. Part E, it's asking what is the horizontal distance from the entry point. Again, fairly simple. All you have to do is multiply this horizontal component of your velocity, which is going to be equal to 10 cosine 30 degrees, times the actual time that it took to get to the point where we're saying where it returns to the entry level. So all you have to do is multiply our time by 2, because since this is a parabolic path, we'll just multiply it by 2, and this will give us the total distance from how much it takes. So it's going to be the horizontal component of the velocity times 2 times 5.7 seconds, 5.7 nanoseconds. And that's going to be approximately 1/10 meters. And it's saying, what is the kinetic energy 4 nanoseconds after entering the electric field? Rather simple. Again, kinetic energy, that's just 1/2 mv squared. That's equal to 0.5, and then the mass, that's 9.1 times 10 to the negative 31 kilograms, and the velocity after entering the electric field, 4.9 seconds, and we multiply that by 10 cosine 32. Kinetic energy 4 seconds after entering. Okay. So let me hold up a second and get space for this. Let me get rid of here. So it's saying on this path, what happens after 4.7 nanoseconds? So we're just going to get our function for both y and x. And what we'll have to do is is we'll have to find both the horizontal component of this velocity and the y component of this velocity. We'll find the magnitude, the total magnitude of this velocity. And after that, what we'll end up having to do is just evaluate the vectors using the Pythagoras. So what we'll end up doing is we have, okay, so at 5.7 nanoseconds, this velocity, that's going to end up being right here. Well, it's going to be constant. So the horizontal component is just going to be 10 cos 30 degrees. But at 4.7 nanoseconds, this value is going to be equal to negative g 4.4 nanoseconds plus 10 sine 30 degrees. And that's just from differentiating the position function, so we get the actual velocity. So then to find this velocity, that's going to be equal to Vx and Vy. I'll put this in terms of Vx and Vy to make things simpler. Well, okay, so we know that this total velocity, that's equal to the square root of Vx squared plus Vy squared. And the kinetic energy, that's equal to 1/2 mv squared. Therefore, it's going to be equal to 0.59.1 times 10 to the negative 31 kilograms. And that's going to be equal to Vx squared plus Vy squared, because the square root is no longer there. That's going to end up being approximately 3.5 times 10 to the negative 17 joules. And we're done.